we're just going to start with a quick recap of last lesson. So let's just see if you remember about speed and distance time graphs. So could you just stick a number onto Spiral now, please, for what your speed will be if you run 1,500 meters in 12 minutes. So here's the formula if you need it. Okay, so there are lots and lots of answers coming in. Some of them are right, some of them are crazy wrong. This is a person who's running. So just ask yourself, seriously, could you be running 125 meters in a second? Surely not. Okay, so the answer is 2.1 or rounds off to 2.1. If you're getting something with 125s in it, just think about where you're going wrong. Could it be that you have not remembered that it's 12 minutes and we always use seconds like in the formula, so you need to convert into seconds. Yeah, 125 per minute EV is a perfectly good unit. Not one we use very often, but it's a perfectly good unit. Okay, let's do another one. Okay, not on Spiral this time because it'll take you too long, but just in your head, start thinking about how you would describe this graph starting at the beginning and working your way through to the end. So how does the story of this person's journey go? I'm just going to give you 30 seconds to think about some keywords, and then I'll go through it with you and you can tell, you can decide yourself how well you did. Okay, so let's have a little think. So at the beginning, it's a straight line, which means it's a constant speed. And also to turn it into velocity, you could tell me that it's moving away from us. Then there's a curving bit, and we spoke at the end of last lesson that curving bits mean that you're getting faster because it's getting steeper and steeper and steeper. Bigger and bigger gradients, so bigger and bigger speed. Then there's another straight bit, but this time it's steeper than the first bit. So you could tell me that it's a faster constant speed. Constant because it's straight. Then the line curves again. This time it's getting shallower and shallower and shallower. So this is slowing down or deceleration. Then finally we get to the stationary bit at the top of the curve. And that means that the distance is neither increasing nor decreasing. So we've got stationary. Then we've got some more curving going on, but this time it's getting steeper. So that's accelerating. And now the object's traveling back towards us because the distance is reducing. Again, it's a straight line, so constant speed, but you could turn it into a velocity by telling me the direction is towards us now. Okay, so that's your quick recap of last lesson, calculating speed and using those keywords when interpreting a distance time graph. Let's also just remind ourselves about the details of velocity, though, because that's what we're going to be spending today's lesson doing. So it's a vector. That means that it has size and direction. So here are some examples. And we're using the sign of the number, the plus or the minus, to represent the direction that we're going in. Plus and minus are opposite directions. So we could say away from us and towards us, or to the left and to the right, up and down, northwards, southwards. It doesn't really matter. It's just two directions that are opposite to each other. Okay, let's switch to today's work then. So last lesson, we were all focused on distance, and we drew graphs of distance. Today, we are just going to note that we could, if we wanted to, not have drawn a graph about where Bertie was at different points during their day, but we could have spoken about the speed, or even better, the velocity at which Bertie was moving at different points in the day. So for those two items there, +4 and -3, we would just have straight horizontal lines, because just like when we had horizontal lines for stationary because the distance wasn't changing, now we would have a horizontal line for constant speed or constant velocity because it's not changing. So it's very, very easy to muddle up distance time graphs and velocity time graphs because they both look similar, but their interpretation is very different. Horizontal line on a distance time graph means not moving at all, but a horizontal line on a velocity time graph means you are moving constant speed. Okay, another difference between velocity time graphs and distance time graphs is often the velocity time graph will need a negative side to the vertical axis because we need the positive velocities for the forwards and the negative velocities for the backwards. Okay, let's see how well you can do at this. So you can put A on spiral, but you'll just have to sketch on a little scrap of paper somewhere the answers to B and C. So I'll just give you 30 seconds for that, but stick your answer for the speed on spiral as soon as you like. I think some of you have forgotten your 6 times table. Oh, your 4 times table or your 12 times table. Okay, so let's have a little look at some answers. So there's the first one. Loads of you getting that right on spiral. Thank you very much. And then graph-wise, we would have a distance that is increasing by 4 meters every single second. And the line will begin at 0 and it will finish at the point that we've been given, which is 48 meters after 12 seconds. So that's the distance time graph, but the velocity time graph is going to look a lot different to that because it's just a constant velocity of 4 meters per second. So that's going to be a horizontal line now at the 4 point on the velocity axis. Just as time ticks by, the velocity just stays the same at 4 meters per second. Okay, we're going to do a little bit of rapid fire on spiral now. I'm going to ask you a series of multiple choice questions to see how your understanding is. All I'm looking for on spiral is a letter. So A, B, C, or D. So first question, on a distance time graph, what does the gradient represent? Could you put an A, a B, a C, or a D on spiral now, please? Okay, it's about half of you have answered. The rest of you just a bit quicker, please. 5, 4, if you don't know, guess. 3, 2, 1. Okay. I'm looking at a screen full of Bs with 1 C and 3 Ds. So it does represent the speed. It doesn't represent the acceleration. So the couple of Ds are wrong. But actually, the best answer is C, the velocity, because gradients can be positive or negative, and we're using that to represent the direction, which is the velocity. So B isn't wrong, but C is better. Okay, let's do another one. Okay, same question, but for a velocity time graph. What do you think it might mean on a sloping graph on a velocity time graph? I'm going to count down from 10, and I want an answer from everyone by the time I get to 0, please. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Okay, the answer is D, which the vast majority of you did get. It is showing that the velocity is getting bigger and bigger and bigger in this picture, which means that it's accelerating. It's getting faster. We're going to come back to acceleration a little bit later on, but just as long as you can recognize it in a graph. Okay, next question. I'm just going to count down from 5 now. So I'm looking for 2 letters this time, please. 2 letters, an A, a B, or a C, and then a D and an E. 5, 4, 3, 2, 1. Okay, most of you have answered. I am seeing a very large number of D's on my screen, which means traveling towards us. That's not correct. Anything above the line is a positive velocity, and that means it's traveling away from us because distance is increasing. So, oh, sorry, I've misread it, haven't I? Yeah, D is the correct answer. It means traveling away from us. Well done. I'll just shut up. And then on a velocity time graph, it's a constant velocity because this is a horizontal line which is staying at the same level. So C's and D's are the correct answers there. Okay, next question. What about this one? So 2 more letters, please, when you're ready. Okay, a very large number of correct answers this time. I think you're getting the hang of it. Okay, so practically everyone has gone for C and E, which is correct. It is constant because it's a horizontal line. The velocity isn't changing. And this time it's below the axis, which means it's a negative velocity. That means it's coming back towards us. Okay, what about this one? Okay, one person has already got the correct answer. Oh, we've got loads of coming in now. Well done. Okay, 3, 2, 1. Okay, I think those of you that are hesitating, you're trying to find a second letter, but this one is a bit of a trick. This one's constant velocity, but the constant velocity is 0, and therefore they're not moving towards us or away from us. So it's just C. That's the only answer this time. Okay, what about this one? Two letters required. Okay, so we've got decelerating because the velocity is coming down, 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 down. You can see that it starts up here and it comes down the velocity axis. So it's getting slower, it's decelerating. But the whole thing is above the axis. The velocity is always positive. It's always traveling away from us. So your answer is B and D. What about that one? Oh, you're banging them out now. I think you've got the hang of this. Lots and lots and lots of A's and D's appearing on the screen. A, because it's accelerating with the velocity getting bigger and bigger and bigger, and away from us because the whole thing is above the axis, so it's a positive velocity. What about this one? Okay, lot more variation in answers this time. Okay, so we have actually only got 5 people with the correct answer. It's tricky, isn't it? When it goes below the axis. Still only got 11 of you with the right answer. Okay, so let me go through it with you. So it's below the axis, so the velocity is always negative, which means it's coming back towards us. So you need to settle on E. But then is it A, B, or C? Well, it's changing, so it's not C. And remember, these are big numbers and zero's in the middle. So when we're heading towards zero, that means that the velocity is getting smaller and smaller and smaller. The speed's getting smaller and smaller and smaller. It's heading towards zero speed. It's decelerating. So your answers are B and E. Okay, last one. See if you can redeem yourself. What's this one doing? 2 letters, please. Okay, I'm getting a flurry of correct answers this time. Much more confident. Okay, got about half of you with the right answer. Oops. Okay, we're there now. So we are accelerating because we're getting away from the zero axis, which means we're getting bigger and bigger and bigger, but in a negative direction, which means we're coming back towards us. So the answer is E, accelerating and towards us, A and E. Very good, well done. Okay. This is where you need to reach for your book, because this is the first point during today's lesson that you actually need to write something down. So we need to have a definition of acceleration the way that we had a definition of speed and velocity. So here is our definition. Acceleration is the change in velocity in 1 second per second. And you will be familiar by now. Say that I know that the velocity is changing by 8 meters per second. In 1 second, then the change is 8. So that's fine. But what if I knew that the change was 8 in 2 seconds? Well, I'd then have to halve it to find out that I was getting the change in just 1 second. So there is a formula that goes with this, and I need you to put that in a box in your book and make it look important, like you did the speed one. But I would just draw your attention to the kind of traffic cone that is in the unit brackets for acceleration. Obviously, don't copy that down. We're going to have to fill that in a second, but it's just something we need to be a little bit careful about. And if you want to save yourself some writing, instead of writing the word change in, you could write a delta if you wanted to with a triangle. So you could write acceleration equals delta V over delta T if you are mathematically inclined. Okay, so you got a formula. Acceleration is change in velocity divided by the time taken. But why am I not giving you the units? So I just need you to clear your head completely. About 5 years ago, some students were surveyed nationally about what was the hardest thing that they ever did in their GCSEs, any of their GCSEs. What was the thing that made their head hurt and the thing that they found most confusing? And obviously, lots of people said lots of different things. But the thing that most commonly came up was the next 5 minutes of your life. So just clear your head. Take a couple of deep breaths, find your calm, happy place, and we'll just pretend that everything's going to be fine. I'm going to take it in tiny, tiny, tiny little baby steps. And so by the end of this, if I'm doing it right, hopefully you'll wonder what all the fuss is about and what all those other students were thinking. Okay, so here we go. Clear your head, unit of acceleration. Okay, remember what the definition is of acceleration. It's how much the speed, or we'll go with speed rather than velocity so that we're not having to worry about the signs at the moment. Acceleration is how much the speed's going to change in a single second. So here's a car. It was traveling at 20 kilometers per hour. And then it accelerated and it ended up traveling at 50 kilometers per hour. And it took 10 seconds to do that. So the first thing we need to work out is how much did it change at all? So it was traveling at 20, it's now traveling at 50. So 50 take away 20 is 30 kilometers per hour. The change in the speed is 30 kilometers per hour. But it did that in 10 seconds, not in 1 second. So we need to divide that by 10 to get the change in a single second. And this gives us the number that the formula you just wrote down would have given you, that the acceleration is 3. But what's the unit? Well, we just divided kilometers per hour by seconds. So the unit is 3 kilometers per hour per second. And I've put the comma in kind of red there to really make you notice it and to really pause when you speak. My speed has changed by 30 kilometers per hour per second. 3 kilometers per hour is a perfectly good change in speed because it's a change in speed, so it needs the unit of speed. So the change in speed is 3 kilometers per hour, but the acceleration is how much it changes per second. So I have to add per second to the end. So the correct unit for the acceleration is 3 kilometers per hour per second. And given that we always write the per as a slash, like here, when we write that down, we would write it like that. 3 km slash h slash s. Now, that is probably not something that you have done very much of in the past. And it should make you think that looks a bit strange and unfamiliar. It's pronounced 3 kilometers per hour per second. But I do need you to pause after the word hour, because if you just say 3 kilometers per hour per second, that just sounds weird. Per hour per second, what's that got? What does that mean? So it's 3 kilometers per hour, that's the speed bit. Per second turns it into the acceleration. So just remember to pause when you're pronouncing it. 3 kilometers per hour per second. That's not the traffic cone bit. I'm going to give you exactly the same question now, but instead of traveling at 20 kilometers per hour, the car's now going to travel at 20 meters per second. It's exactly the same question, apart from the units. So the numbers bit is the same. 50 take away 20 is 30. And 30 divided by 10 is 3. But in terms of units, our 50 is a 50 meters per second. Our 20 is a 20 meters per second. So now we've got 30 meters per second as the change in speed. And now what we've done is we've got our speed is changing by 3 meters per second. And again, vital that you pause when you pronounce that. Otherwise, you're just going to say meters per second, which is just like you've repeated yourself. So remember to pause. Your speed is changing by 3 meters per second per second. How would we write that? Well, even more confusingly, we'd write it like that. m/s/s, which really should make you feel uncomfortable. But that's still not the traffic cone bit, because in maths, if you were to write algebra as algebraic m, and then that slash means divide, divided by algebraic s, well, if you then divided by another s, you'd be dividing by s twice, which is dividing by s squared. And so that is your unit of acceleration, meters per second squared. I don't know anyone who likes that. Everybody doesn't like that. The examiners know you don't like it as well. It comes up on every exam paper. There will be marks available for remembering to write that little 2 next to that S. And every year when I teach this, I take it in very little baby steps and I lay it out as simply as I can that there is a 2 on the S in the unit of acceleration. But every year I then test students, I give them the end of topic test, and I know a third of the class will forget what the unit of acceleration is. Make sure that that's not you. So go back to your formula in your book and insert yourself a unit now for acceleration. It's pronounced meters per second per second. If you want to, you can pronounce it meter per second squared or meters per second, but I personally feel that either of the latter two pronunciations makes it seem confusing and kind of puts some distance between you and what it means. So I encourage you very much so to pronounce that unit meters per second with a pause in the middle. So here's an example of that in action. So here's a car. It's traveling at 12 meters per second. And then a little bit later, it's traveling at 54 meters per second. And that took 6 seconds. Could you please, on spiral, tell me what you think the acceleration is and make sure you get the units on. Don't worry about making the little 2 go up in the air, just write S2. Okay, so what do you think the acceleration is with a unit, please? First little bit is 42, but then you need to divide it by 6. So yeah, the answer is, as on the screen, 7 meters per second. Kieran has put a lot of dots in his to make us pause. Okay. Well done. Miles per hour per second. No, not miles per hour per second. Okay, so that's, like I said, traditionally very difficult, that unit. I hope to have done it so utterly slowly and carefully that you personally don't think that there's anything wrong with that. If that's the case, then that's good. Okay, one last thing. Acceleration, like velocity, turns out to be a vector in that it has a direction associated with it. But here's where we need to go a little bit abstract on the word direction. In everyday life, direction means a physical direction that you could point in with your finger and go over there in that direction. But more abstractly, direction just means what way are things going in. And that can include numbers getting bigger and bigger and bigger. They're going in an increasing direction. And numbers getting smaller and smaller and smaller, they're going in a decreasing direction. So we can talk about acceleration being an increasing speed or a decreasing speed, whether we're getting faster or slower. So although earlier in today's lesson, we were using the word decelerate to mean get slower, well, actually, a deceleration is just what happens when the speed changes in a downwards direction, when the speed is decreasing. So we don't actually need the word decelerate at all, although I'm sure we're not going to get rid of it from everyday language. We have got rid of it from physics. We don't need decelerations. Any change in speed is an acceleration. Now, that needs some thinking about maybe for a second. So this car that's on the screen in front of you, that's traveling at 54 meters per second, and then 6 seconds later is traveling at 12 meters per second. In everyday language, you would say the car was decelerating. But in physics, you would say the car is accelerating. It's just that the acceleration is going to have a minus sign in it, because 12 take away 54 is minus 42. And minus 42 divided by 6 is minus 7. So this car really is accelerating. Its speed is changing by minus 7 meters per second. Negative accelerations are decelerations. Acceleration is a vector, just like velocity. Heady stuff. Today's lesson, therefore, has contained not one, but two abstract concepts. How will you cope? Well, over the next couple of lessons, we're going to develop our idea of acceleration and also velocity time graphs, actually, in more detail. We'll do that next lesson. So there will be more time to practice then. And then the lesson after next, I'm going to put the entire hour to one side to just do questions to make sure that we can apply all of this learning that we've been doing and the formulae that we've been using. So we're going to get plenty of practice, but given that we are now, what, 10, 15 minutes off the end of the lesson, I thought maybe you'd like to finish with something a little bit less taxing. So these are some distance and velocity-based games, which you might think are going to be boring, but they are weirdly addictive. I used to have one as well, a third game as well, but it was a Flash-based game. And Flash, you might know, is a technology that was retired at the start of this year. So it doesn't work anymore. I love that game. People would get hooked on it, and definitely an addictive one. But these two games are also addictive. So you can either open up the PowerPoint from Classroom and just click on those images, or the links are just there on the Google Classroom post.